Unit 2. This is lesson 2.1 or 2.1 in your book. So now we're going to kind of, hopefully this is familiar to you, but we have worked on this. Okay, f of a plus h minus f of a all over h, and that is what we're going to use as the connection with derivatives. Okay, so kind of a summary, derivative is defined as a limit and arises when finding a tangent slopes or a rate of change. So we use this to find tangent slopes. Okay, and that's what a derivative is, so we use it, derivatives are used to find tangent slopes, in other words. Okay, so this is a long way of looking at a derivative, but again, like I told you, today you're going to do the long way, sorry, but after today we're going to learn different rules for doing the derivative quicker. Okay, and it'll actually be kind of nice. And again, the limit has to exist to do it, and we can still use this. This kind of, see how it says f prime of a? That's kind of calc notation for derivative. Okay, that might be something you want to write down to remember. When you have the f prime of a or f prime of a function, that's the derivative of the function. So the good news is there's nothing super new today. So that can be a good way to start a Monday, right? Okay, so example 1. So if we're trying to take the derivative, now see, we're taking a step further. We want to find the derivative at 4. Now it's not necessarily a step further. We're just telling us what x is, right? Because it's function notation. So we know x is 4. But what we're going to do is we're still going to do our f of a plus h minus f of a all over h as the limit of h approaches 0. But we're going to do it for, we want to find the limit of f prime of 4. So this is f prime. So that means it wants you to do the derivative and plug 4 in. So to do the derivative, we're going to use the limit definition for now. By doing the limit definition, we're going to have, it's going to be a little bit long here. So it's going to be 2 times a plus h squared, I put it in for x there, minus 5 times a plus h plus 6 minus f of a, so f of a, plug the 4 in. Okay, that's going to be, if I put a 4 in, that's 16 times 2 is 32, minus 20 plus 6. So that's going to be 12, that's going to be 18. All over h. Now we're just doing the simplifying game. Yeah. Yes. When I plugged 4 in for x, I got 18. That's correct. In other words, something else to realize, that means that 418 is the point that we're going tangent through on our given graph. Okay. But anyways, so now we're going to simplify. So we're going to get 2a squared. If I FOIL that out, I'm going to get 2ah, 4ah, and 2h squared. Okay, plus 6 minus 18. Okay, we do know what a is, so we can go ahead and plug a in. Now I could have done it before, I just forgot, but I guess it doesn't really matter. So I know what a is for us right now. A for us is still 4. So 4 squared is 16, times 2 is 32. 4 times 4 is 16h, plus 2h squared, which we don't know. Okay, plus 6 minus 18. I think I'm missing something here. 6, 32, 6h, 2h squared. This right here is wrong. What's this? 2h. Say that again. I have 2h squared. So I'm missing, what am I missing here? Oh, yeah. I missed this guy. Sorry, I was like, I'm missing a whole thing. My bad. Okay, so, sorry, so it's going to be minus 5a up here, minus 5h, plus 6, minus 18. I knew I was missing two things. Okay, so minus 5a, that's going to be 5 times 4 is 20, so minus 20. Okay, minus 5h, plus 6, minus 18. There we go. Sorry. This is still all over h. And still, we're still trying to get our h's to cancel. We're still playing the same limit game we've been playing all last chapter, so as h goes to 0. So what we want to do is, the reason I needed that, 32 minus 20 is 12, plus 6 is what? 18, minus 18, so they all cancel. And that was the hope. We'd like to see the constants cancel. So these all combine to make 0. So now we have just h's on top, which is really good because now we can go ahead and simplify and get the h off the bottom. So 2h squared on top, 16 minus 5 is 11. So we can pull an h out, and we get the h's to cancel. So now we can do the limit of 2h plus 11, so we get 11. Okay. So 11 is the tangent slope there. Or 11 is the derivative. Yeah, so in other words, yeah, using a limit to find the tangent slope is the derivative, yeah. Okay. All right. Next. All right, so by comparing the definition of the derivative and the definition in Chapter 1, we have the following. Interpretations of derivative as a slope of a tangent, so like you just said, which is taking the limit as f of a is approaching whatever. Then we have as a rate of change, so we have the instantaneous thing we did last chapter, and we have the average. Okay, but we talked for specific to limits, instantaneous helped us with limits. We can find averages just using our normal slope formula. Okay. So whenever we're trying to find instantaneous, we can do that, and this is what we're going to use the most for, and this is the applied stuff, and this is where it's kind of, I guess, magical if you want, but kind of a very smooth way of finding velocities and how the rate of change happens with different objects or gravity and stuff like that. Derivatives helps us accomplish that quickly, so it's kind of nice. Okay, okay, and example 2. Okay, so find the derivative of f of x equals x squared minus 3x at any number a. Then use it to find the slopes of tangents of the parabola when x is 1, 2, 3, and 4. So what we're going to do is we're going to find the generic slope. Okay, so like we're going to find just the generic equation we'd use to plug in 1, 2, 3, and 4. So what's going to happen is we're going to do just a is going to be a. So you're going to do, we want to do f prime of a equals, we're still going to do limit h approaches 0, and then we have f of a plus h minus f of a all over h. And so what we're going to do is, it's going to be messy, but we're just going to go ahead and plug a plus h in for x. So I have a plus h squared minus 3 times a plus h. And I'm going to subtract just plugging the a in for x. So then I have minus a squared minus 3 times a, which is 3a. Okay, so now let's go ahead and look at it. This FOILed out, the a plus h FOILed out, is going to be a squared plus 2ah plus h squared. Distribute the negative 3, negative 3a minus 3h. I have a negative a squared, and a negative times a negative is a positive. Okay, everybody staying with me? And you're going to kind of recognize the pattern now. So we're not going to have to do this every time after today, but it's good for you to understand where this comes from. Look, we have these type of nice things that happen every time with the pattern. A squareds are gone. Constants are gone. And so what I have left, everything that's left, it has a what? An H. So we're happy about that because we're all over H still. Okay, so that leaves me with, let's go back to where we're at here. So I have H squared plus 2AH minus 3H all over H. So if I pull an H out, that's going to give me H minus 2A minus 3. Okay, so now we can evaluate this limit. Oh, plus 2A, yep, thank you. I just saw that in my notes right when you said that. Plus. Okay, so what happens is this H is gone when I plug 0 in, so your equation to figure out your slope for this problem is 2A minus 3. That's your equation to figure out the tangent slope. So now, if I want to find it for x, I want to find f prime. If I want to find f prime of 1, f prime of 2, f prime of 3, and f prime of 4, I simply would just plug it in right here. So 1 is 2 times 1 minus 3, negative 1. 2 is 2 times 2 minus 3, is 1. 3 is 3, and 4 is 5. Okay, so those are all the different slopes, and it makes sense because the slope's going to change as that, because that's a parabola, as that parabola is going to kind of alter. So just maybe a short illustration. If I factored this, it'd be x times x minus 3, so I have 0 and 3 is where this parabola goes through. So it goes like this. So when I'm at negative 1, the slope is negative 1. So that means it'd be coming downwards. When I get to, I get to 1. Oh, I was at 1, sorry. At 1, the slope is 1. No, negative 1. That makes sense. Okay, sorry. Let's look here. So when I'm at 1, right here, see how it hits? See how that parabola is like going, if I get to go through that, I'd be going in a negative direction. That's why it's negative 1. And then if I hit 2, now it's turned. So now it's going through it in a positive direction. So now it's a positive 1. And then if I hit 3, it goes through it even steeper at 3. And then 4 would be way up here, even steeper at 5. So it's kind of a good illustration of how that thing rotates around the parabola in terms of its slopes to hit the tangent-wise. Okay, does that make sense? Okay. All right. Let's go on to the next one. All right, so the derivative of a function, or as a function, derivative of a function f at a is a number f prime of a. So that's what we were just doing. F prime of a means the derivative at a. But if we let a vary over the domain of f, we can change our point of view and regard f prime as a function. So what that means is that we can just, like we just got the function 2a minus, what was that? 2a minus 3. That's the function that represents the change of that original function they gave us, the tangent slope of that original function. Okay, so that 2a minus 3 we got last time is what we could regard as a function of change of that slope for that function. Okay, that's what they're kind of talking about here, being general. Okay, so the domain of the new function f prime is set of all numbers of x for which the limit exists. Since f of x occurs in the expression for f prime of x, the domain of f prime will always be a subset of the domain. So that just means that whatever is allowed for x would be allowed for that subset. So the limit would have to exist, because if the limit didn't exist, then there would probably be some type of domain issue. Okay, is there something we couldn't have for x, or being on the bottom? And every time where's limits we had that were D and E. Okay. So you have to have defined at that limit, which we already have that written down. Okay, so let's look at this one. You might be kind of confused in the domain part, but the next two examples are going to illustrate that better than me really talking about it. So, okay, so find the derivative function of x squared. So fairly simple. We're just trying to find the derivative of x squared. So we're just going to stay with our pattern. And again, tomorrow this derivative is going to be super simple. So I know today we're doing the long day, but you're going to be fine. Okay, or it says f of x. Sorry, I put a's. Okay, so what we're going to get is, we're going to get a plus h squared minus a squared all over h. That then simplifies to a squared plus 2ah plus h squared minus a squared. Whoops, not squared, just h. Okay, we see that the a squareds are gone. What we have left only has h's, so that's good. So we can pull an h out. So it's going to be h times, I'm going to switch these here. Like so. The h's cancel. Now we can do the limit. So we get 2a. So 2a represents the function of f prime, okay, the derivative. 2a represents the derivative of that function. Now what we want to do is, what is the domain of 2a? If I want to find what's the domain for a, is there anything that we're limited to have there? There's nothing we're limited to have there. That's correct. So it's all real numbers. Okay, so the domain for this right here is just all real numbers. It's kind of a simple one. And then we're going to get one here with a radical next, and then we can assume where that's going to go. Okay, let's go to the second part here. Okay, so example 4. Okay, now f of x is square root x plus 2. Find f prime and states the domains of f and f prime. So we want to look at the domains of the original and the derivative. Okay, so we're still going to do the derivative, so we're still going to go limit h goes to 0. And you can put x's in. The notes started doing x's. So what I mean by that is they started doing f of x plus h. You can use a. Like that. So that gives me, if I put x plus h in for x, that gives me square root x plus h plus 2 minus x plus 2 all over h. Okay, so what strategy you want to do here? Because the problem right now is the h in the bottom. I have nothing up here to cancel the h with. Okay, yeah, conjugate the top, right? We want to do the conjugate to the denominator. This is where, when we're doing our pre-calc review, a lot of us are like, why would I ever rationalize or do the conjugate to the top? This is why. Okay, to manipulate things to work in our favor. So we're going to go x plus h plus 2 plus x plus 2. We're going to do that to the bottom as well. Do not distribute the bottom out. Here, let me rewrite that. Yeah, I know. Sorry. Let's try this here. I'll just write it right here. So we have the original minus, okay, we're going to times it by plus. Like that. All right. So top, remember it's a conjugate, so it's going to be nice. That's going to make x plus h plus 2. That's going to make minus, minus x minus 2. So you can see what happens at the top. X's cancel, 2's cancel. We're left with just an h, and that was the goal. So on the top, we're just going to have an h with this stuff on the bottom. So my h's cancel now. Say it again. These two? No, because in order to combine radicals with addition, they have to be the same radican. So by radical rules, these are different. So it'd be like, you can't add a root 2 plus a root 3, right? So you can't add these together either. Okay, and now we can actually take the limit of it. So it's going to be 1 over x plus h plus 2 plus x plus 2. Okay, if I put 0 in, that's going to give me, now what you're saying is right, Morgan, because I put a 0 in for h, I'll have 2x plus 2's. So then I can put them together. So what I'm saying is, what she just asked was, can I put these together? Now I can't, but if I put a 0 in, now they're both x plus 2, so I have 2x plus 2's. So your limit is simply 1 over 2 root x plus 2. And they want us to find the domain of the original and what afterwards. Okay, so what's the difference between the domain of the original and the domain of the second one? Yeah, Emily? Right here? So when I put a 0 here for h, because we're doing the limit now, that made it, so I kind of skipped a step, but that made it, so now I have x plus 2 plus x plus 2, and there's 2 of them, so I just wrote 2x plus 2. Okay? But what's the difference between the domain at the beginning and the domain at the end? Okay, yeah, essentially, yeah. So the second one, so we'll say domain of f prime. What's the domain of f prime? What's the domain of f prime? Jeremy, what do you think? What's the domain of f prime? This guy here. What's the domain of this guy here? Greater than 2. Why not greater than equal to? Which gives us 0 on the bottom, right? So the domain of this one is greater than 2. Yes, negative 2. Thank you. Okay. The domain of the one up here is greater than equal to 2 because we could have 0 for this one. That's the only difference. So f of x is greater than equal to negative 2. That's it. Sorry. This one's just f of x, not f prime. Man, these are really bad today. Sorry. Let's rewrite this. All right. Domain f prime of x, x greater than negative 2, f of x greater than equal to negative 2. Not much better, but oh well, I tried. Okay. All right. Let's see here. Let's do a little challenging. For example, 5. Got a fraction, so we do have some domain issues. Definitely can't have, would that be 2/3? Okay, we want to be able to have 2/3 on the bottom in the beginning. But if we're doing this just like we've been doing, might need 2 pages for this, but we'll see. All right, so we're going to go, still going to do f of x plus h minus f of x all over h still. So it's going to look like, the first one, I got to put the x plus h into 2 spots. So it's going to be x plus h plus 1 all over 3 times x plus h minus 2. Okay, and then minus just this again. This is where in this course that it's all over h, that you're going to have to be really good with your fraction stuff. Okay. Okay, so I'm going to distribute the bottom here. So I'm going to get x plus h plus 1, 3x plus 3h minus 2. Okay. Any ideas on what to do now? Multiply the 1 by 3h? Close. Well, you're kind of doing an illegal fraction move. You can't because you can't multiply into 3h and it's not going to come in here as a plus, right? And that's a common mistake, and that's okay. Kate, did you have something? Yeah. Right, times them both by themselves. Okay, so as you're hoping not, you do need to do all of it. Yeah, this is where when you get done with something in here, you feel pretty confident about yourself. Unless you get it wrong, then you feel really depressed. Okay? So we did just by each other. Just times them by each other is all we did. Okay, so now you're just going to distribute and do all this stuff. Do not do the bottom yet. Leave the bottom for now. Let's see what happens. We might get lucky. Some things might cancel. Always do the bottom last. Okay, so if I distribute these, I get 3x squared, 3xh, 3x, negative 2x, negative 2h, negative 2. Okay. Now, this is what I'm going to do on this part. Okay. Since it's a minus, everything I get doing this, I'm going to put the opposite sign. Is that okay? Everything I get, I'm going to put the opposite sign. So x times 3x is minus 3x squared. I'm putting a minus. Minus 3xh. Negative 2x plus 2x. Minus 3x. Minus 3h. Ooh, just enough room. Plus 2. All right. You're confused?
Is this the bottom?
No, the top. We're leaving the bottom as is, and we're going to simplify the top first.
But like of the whole thing?
Yeah, okay, sorry. This is the top of the whole thing, but we're doing the tops of the fractions on top. Because everything's over h. The whole thing's over h.
Okay, so the lines on it, the one above that is really just the top of it again?
Yes, so I wrote this again, yeah. This right here is this here.
Okay.
Good question. So yeah, just keep it organized. We're doing the top of the top. Okay, so now let's go in through and cancel what we can cancel. I got 3x squared, I got negative 3x squared. 3xh, I got a negative 3xh. 3x, I got a negative 3x. Negative 2x, I got a positive 2x. Negative 2, I got a positive 2. See, it's not that bad. Okay, so now we have negative 2h and negative 3h, right? So that gives me, that's why I told you not to cancel those yet. Negative 2h, sorry, I can go ahead and make that negative 5h, right? So negative 5h is what all that worked out to be on top. All of that's still over these guys. 3x minus 2 times 3x plus 3h minus 2. But if this is all over h, where's that h really at in this fraction? The bottom, yeah, it's just right here. So we can just slide that up real quick using our fraction skills. H cancels, H cancels. So now we have limit as h goes to 0 of negative 5 over 3x minus 1. That's a 2. 3x minus 2. Say that again. It will be. You're right, because the h will go away, right? I'm just not doing that part yet. 3x plus 3h minus 2. And then like Morgan just said, this h, when I put the 0 in, will go away. So it will be negative 5 over 3x minus 2 squared. Because this h right here will go away, and that's 3x, this is the minus 2, geez, right there. So that is what the derivative of this guy is. Congratulations, that was good. You made it. We got on one page too. All right. Okay, now we're going to look at a little picture here, and this is more of a concept thing, so just really focus here. So it says, use the given graph of fx to sketch the graph of f prime of x. So with that being said, can anybody think of a strategy or something that we know or we could use to help us? Because we know that tangent means it goes through it at one point, right? So what do you think are critical or very important points when looking at the original to figure out what the graph of the derivative would look like? Nope, not as much. It's not bad, but not as much. Yes, good. Max mins are crucial because if this is the maximum, if that's the maximum, what's the line slope going to be going through there? Straight across. A straight across is a slope of what? 0. Does that make sense? So here, just those 3 points, okay, are crucial points. Okay, so the graph, I'll do it in blue here, of the, you're going to kind of graph the slopes, the tangent slopes, what that graph would look like. So if that's 0, then I would have a point here at 0 for that spot. Because at, what is that? At negative 2, the tangent slope is 0. So I'm going to put a slope, dot there at 0 for my new graph for the f prime. Same thing here. Same thing here. This one? Yeah, but we're talking about tangent at a point. Yes, this would go through the parabola again, but from this point, that's the only way it'd be tangent. I see what you're saying, though. Okay. And you still will steal a couple other things. You'll learn these kind of a little bit later, but these will, this essentially will flip your y-intercept. So I guess that was important. Sorry, you were correct on that. And you will still keep your x-intercepts. So it'll be now, no, you won't keep your x-intercepts. That's false. Sorry. So the new one's going to be roughly like this. So that is the rough sketch of what the derivative function would look like. And I wonder if it's on the next slide, but okay, we're just going to talk about a couple notation things really quickly, and then we'll have one more example, and that's it. So the key on these is it's focused on the change of direction. Max, min, max. Those points give you zeros for the tangent slope. All right, so a couple things in terms of notation. You don't have to write all this down. What I would write down is whenever you see dy dx, that means f prime. dy over dx means derivative of y with respect to x. So that means you're taking the derivative of a function with respect to x. Okay, we will get, as we get further in this class, we will do dx dy. Okay, that's when things get a little more complicated, but when you see dx dy, dy dx, you're thinking derivative. Okay? So from earlier, y was x squared. dy of dx, that means derivative of y with respect to x, we got 2x. Remember, back in our previous examples? So that's how you'd write the notation. Same thing with these three. Okay? So these ones, if you want to write these down, maybe as examples, I'll go ahead and wait, but yeah. Okay, so for now, symbol dyx should not be regarded as a ratio. It is just a synonym for f prime of x. So that just means, just again, when you see this, think about derivative. And we can use this in different notations with the same respects, like with velocity. It could be d of s over d of time, okay, just derivative of s with respect to t. So that would just be like, as t determines your speed, so it's just another way you could write that, and we'll use these in our applied problems later. And then a slight variation, we'll talk about when you can use this, but when we get to these, we're going to be having to solve for dy dx, and sometimes writing it in this notation can help us. So all this is essentially just pulling the y off as an f of x. Sometimes that can help you. And again, these are just kind of different tools and manipulations we're going to use to help us get through some more difficult problems. So we'll come back to this thing later. That's more of just kind of a basic interview so you've seen that before. Okay. All right. Do we have... Okay, and think of d of dx as a differentiation operator. This we could write d of dx of x squared is 2x. So what that is, they wrote the f of x next to it. Okay, so because we have f of x from earlier was x squared. So that's all they're doing here. They're just showing us another way of writing derivative. Okay, sometimes symbols d or d of x are used as differentiation operators. So these can also stand for derivative. Like if you're doing derivative function, you can put d of x if you want, and that is fine as well, like they've done here. Kind of all these things are the same. Might be something right down there, just so you're familiar with all of them. And 13. Okay, differentiable functions. A function of f is said to be differentiable if f prime of a exists. So you can differentiate, take the derivative, if there is such thing as an f prime of a. It is called differentiable on an interval if it's differentiable at every number in the interval. Example 3, we saw that f of x equals x squared. It's differentiable on R for everything. So that meant that the derivative was 2x, and our domain was all real for both. Right? There wasn't a change in what you can be. But when we did this one, there was a change. It went from x greater than or equal to -2 to just x greater than -2. Okay, so that would be an example of where it was a differentiable for all of it from the original. But it still existed, so it still was differentiable. The next one we're going to do right now, we're going to prove that the next one is not differentiable. Okay, so show the function absolute value of x is not differentiable at 0. So what we're going to do is, we're going to go ahead and just do our regular stuff we've been doing. So we're doing it at 0, so that's our a, don't be confused. So we're going to do f prime, our derivative, is limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. Okay, well, f of 0, what's the absolute value of 0? So it just goes away. So we're left with 0, that's nothing. So we're left with f of h over h. Okay, f of h is, if I just plug an h in for x, that's just absolute value of h over h. Still have a 0 over 0 problem. I can't cancel because it's absolute value. It's a little bit different. So what I have to do is, since absolute value accounts for what? The positive and negative, I want to look at it from the left and the right. So we're going to look at it from our one-sided limits in 1, 3. We're going to do limit as h approaches, because this is two pieces. Do we understand that? This is h greater than 0, h less than 0. Like it's for both of them, for negative and a positive h. It's going to be the same thing. So we're going to do is h approaches 0 from the right for this.
Jim, your class changed.
So if I'm coming from the right, what's a number bigger than 0, Jeremy? 1. So if I put a 1 in, I'm going to get what? 1 over 1. If I put a 2 in, I'm going to get 2 over 2. If I put a 3 in, I'm going to get 3 over 3. So bottom line, the limit is 1 coming from the right. Right? So coming from the left, Kate, give me a number smaller than 0. Negative 1, right? So I'd get, if I put in negative 1 for h, I would get 1 over negative 1. So we see the issue, okay? The limit doesn't exist by our definition. Therefore, f prime of x does not exist. Okay, does anybody want to take a guess why as we finish up here? I'll draw the picture here. I hope we remember from Math 20. That's what absolute value looks like. Why is that not differentiable at 0? It's switching directions and what would you say? It's pointy. So it's not rounded. It's not a nice smooth transition. It's pointed. So it's to the point of where that's like they're two graphs joined together, that you can't have a tangent line to that corner. You can't take tangent of corners. Okay, and that's it for today, finally.